Reliable LLM serving starts with treating GPU memory as a shared, protected resource. In this module, we'll connect admission control, workload isolation, context limits, and OOM recovery into one operating model for keeping production inference stable under pressure. So far, we've moved from diagnosing production failures to redesigning the serving stack to adding reliability controls such as caching, breakers, deadlines, and load shedding. Now we address a failure that can still take down the system: GPU memory overload. The focus is isolation and safe concurrency, setting us up for observability in Module 4. CPU memory pressure often gives you warning signs. Latency rises, swapping increases, and throughput gradually degrades. GPU memory is less forgiving. A worker has to fit model weights, KV cache, activations, batch overhead, fragmentation, and runtime reservations all at once. Long prompts and high max token limits can expand the KV cache quickly, especially when many requests run concurrently. Once capacity is crossed, failure is often abrupt. The worker crashes, the batch is lost, and retries spill into neighboring workers. That is why reliability depends on predicting memory before admission, not simply restarting after an out-of-memory event. Safe concurrency should be enforced before traffic reaches expensive GPU workers. The inference gateway acts as the control plane, checking each request against several gates. Global limits protect the platform from aggregate overload. Per-model limits reflect that a small embedding model and a long-context generative model use very different amounts of capacity. Pertinent limits prevent one customer or workload from crowding out others. Priority limits preserve headroom for interactive, premium, or business-critical requests. When a request cannot be admitted safely, it should be queued, redirected to cache or fallback, or rejected quickly. Concurrency limits are measured safety boundaries, not guessed thread counts. Start by load testing each model with realistic prompt lengths, output lengths, and batch sizes. Find the point where latency rises, memory headroom shrinks, or failure risk appears. Then set the configured cap below that point, leaving room for bursts and variance. Separate limits by traffic type as well, because interactive requests, streaming responses, and batch jobs stress the system differently. Finally, recalibrate whenever the model, quantization, VLLM settings, or hardware changes. A safe limit is only safe for the environment where it was tested. In a shared LLM platform, fairness has to be designed. Each tenant needs explicit limits for concurrent requests, tokens in flight, and queue depth. Traffic should also be separated by priority, so premium interactive work is not stuck behind batch jobs or experiments. Some capacity should remain reserved for critical paths, even when the system is busy. When a tenant exceeds its allowance, the platform should return clear back pressure, such as retry later, instead of allowing GPU saturation to slow down everyone. A request is not a fixed-size unit of work. 10 short prompts may be easy for the GPU, while one long context prompt can fill the KV cache and create real memory pressure. That is why concurrency should also be measured in tokens in flight. Prompt tokens already loaded, plus expected output tokens across the active batch. Admission control can then enforce token budgets per model pool, tenant, or priority class. Request limits still matter, but they are a coarse guardrail. Token limits add the missing weight. So long requests are handled carefully before they become out-of-memory failures. Serving pool isolation is blast radius control. Interactive requests need predictable latency, while batch, long context, experimental, and evaluation workloads can consume GPUs in uneven ways. Rather than letting all traffic compete in one shared queue, route requests by tenant tier, model version, workload type, and SLO. Keep core production paths on stable, capacity-managed replicas. Send high-risk or specialized traffic to dedicated nodes where slowdowns are contained. Premium traffic may also justify its own protected pool. The goal is straightforward: protect reliability for users while still supporting expensive and experimental workloads safely. One common failure pattern is letting nightly summarization jobs share capacity with live chat traffic. Their long prompts create large KV caches, and their runtime holds GPU memory long after short requests should have finished. The fix is isolation. Route long context traffic to pools sized for cache pressure, and send batch work through queues with lower priority, admission thresholds, token caps, and timeouts. Before isolation, P95 latency spiked and ohms cascaded. After isolation, interactive slots stayed available, queue depth became visible, and recovery was a controlled drain down. Premium tenants and experimental models both need isolation, but for different reasons. Premium traffic needs protection. Reserved capacity, tighter SLOs, and dedicated failover reduce the chance that a high-value customer is affected by shared contention. Experimental traffic needs containment. New models should prove reliability in a sandbox before they touch stable production demand. Canary pools connect these worlds safely, allowing small, controlled exposure while preserving the main serving fleet. The practical rule is to allocate capacity according to business value, risk, and operational maturity. The best time to protect memory is before the request reaches inference. Treat every API call as an admission decision. Count prompt tokens, check requested max tokens, and compare the total against the model's context window and the tenant's policy. If the request is too large, take an explicit action. Reject it, truncate safe sections, summarize, or route it to a model with a larger window. Return clear limits to clients as well. That lets applications adapt gracefully instead of failing late, after GPU memory is already committed. Long context usually grows in two places: conversation history and retrieved documents. The safer pattern is to bound both deliberately. First, count tokens before building the prompt, so oversized inputs are visible early. Then compress older chat turns into a short summary that preserves decisions, preferences, and unresolved tasks. Next, filter retrieved material using top K, token limits, diversity, and relevance thresholds. Finally, use a prompt template that reserves space for system instructions, the user request, and the answer. The goal is not more context. It is the smallest context that is still useful. Generated tokens are not free. Every extra token stays in the active sequence, grows the KV cache, and keeps the request occupying compute longer. Production systems should budget output length deliberately. A classifier may need only 32 tokens, extraction might need 256, summaries 512, and open-ended chat perhaps 1024, each with separate hard maximums. Set defaults by endpoint, model, tenant, and priority. Then reject or clamp unsafe client parameters before they reach the model server. Smaller caps usually improve tail latency, reduce streaming time, and limit memory growth. The exact numbers are policy choices, validated with load tests. Even strong prevention will not eliminate every out-of-memory event, so recovery must be automated and conservative. Start by detecting the failure through health checks, server errors, GPU memory metrics, or rising request failures. Then mark the pod unhealthy and drain traffic before restarting it, so users are not routed into a crashing instance. If a model pool is degraded, open a circuit breaker and route to fallback capacity or simpler models. After restart, warm the model, verify capacity, and rejoin gradually. The goal is controlled degradation, not cascading failure. The main takeaway is simple. Protect the GPU before requests reach it. Layer admission controls, separate risky workloads into dedicated pools, and keep context growth bounded with truncation, retrieval limits, summaries, and output caps. Then make recovery predictable. In Module 4, we'll add observability, traces, dashboards, alerts, SLOs, drift signals, and cost attribution, so these controls can keep improving over time.